Hello, AP Chem students, and welcome to topic 7.9, Le Chatelier's principle. The learning objective for today is 7.9.a, identify the response of a system at equilibrium to an external stress using Le Chatelier's principle. Okay, so Le Chatelier's principle says that, it addresses what happens when a system at equilibrium experiences a change. So you've got equilibrium, things are trucking along, and then you do something to the system. We call that the stress. So when any change in concentration, pressure, volume, or temperature is imposed on a system that's at equilibrium, the system responds by attaining a new equilibrium condition that minimizes the impact of the imposed change. There's a little typo there, sorry about that. So remember that if a solid or a liquid is added or removed, there is no change because liquids and solids are not part of the equilibrium expression. So you can kind of see in my fun little graphic here, if you remove that, then what's going to happen is that your equilibrium will shift and then it will proceed to minimize that shift. So if a system at equilibrium is exposed to a stress, the system will shift so as to minimize that stress. Okay, so let's talk about the different stresses that you can have. First of all, you could have a change in concentration. So if a reactant is added, the reaction quotient, Q, will be unbalanced and the rate of the forward reaction will increase to consume some of the additional reactants, thus turning them into products and reestablishing equilibrium. Hopefully my little graphic is going to start moving here in a second. We call this proceeding towards the right or proceeding towards the products. I prefer the word proceedings to shift because proceedings is always correct. So we would say shift if you are at equilibrium and then you disrupt it and it responds. That would be a shift. So in discussing Le Chatelier's principle, it is completely correct to use the term shift. However, sometimes what we actually mean is that something that's not at equilibrium, responds to a stress. And then you wouldn't say shift because it's not at equilibrium yet. Okay, and so in that case, we're not really talking about responding to a stress as much as it is proceeding in a certain direction because of the conditions. Like you don't have one of the reactants or something like that. But it's not technically correct to say shift unless you have attained equilibrium, right? And that's going to become important when we get to Unit 9, so we'll talk about it more later. If we add more products, then we would shift to the left. We would increase the concentration. So we would shift to the left because that is the opposite of what we did up here. So if you increase concentration, you shift away from that species. If you decrease concentration, you shift toward that species. Now, I have a little caveat here. I've gone into a discussion of Q versus K in this topic, and that's actually the next topic. So there's a little bit of blending of the topics here in my videos, and that is my mistake. If you want to say that, it makes sense to me to introduce the Q versus K conversation here. I will do a follow-up video on reaction 710 just to remind you of the Q versus K consideration, but I am going into pretty great depth with that in this video as well. So here's another stress for you if we change the temperature. So when a change in temperature of a system occurs, the equilibrium will shift according to its thermodynamics. So if we have this reaction, let me move my face. If we have this reaction here, you can see that our delta H is -92, which makes this an exothermic reaction. So increasing the temperature will shift the equilibrium in the direction of the endothermic reaction. Okay, the reason for that, if you are increasing the temperature of the system, you're going to shift in the direction that's going to consume that extra temperature, if you want to think of it in that way. So delta H is positive. You can think of heat as a reactant. So endothermic reactions will, so if you increase the temperature and you have an endothermic reaction, you're going to shift towards the products, okay? Decreasing or lowering the temperature will shift the equilibrium in the direction of the exothermic reaction. So if we look at our reaction example here, you can see that what happens here when the reaction mixture is heated, we increase the temperature. This is an exothermic reaction, and so what happens is it turns around and goes in the endothermic direction. And you can see that because the reverse reaction rate immediately spikes. And so this would be the point at which that temperature is increased. And then you can see that we are going to reestablish equilibrium. that's rate versus time. If we look at this as concentration versus time, this is the opposite situation where it's cooled. And so at this point, you can see that because it's cooling, we are actually increasing the forward reaction and making more of the product. We're consuming the reactants in that process. And so this is how it would respond to a decrease in temperature. Delta H is negative. You can think of heat as a product. So in thinking about Q versus K, really important for you to understand that temperature is different because temperature does not impact your Q. Temperature impacts your K. So K changes when you have a change in temperature. And so that's what you have to think about. That is different with the Q versus K consideration. Okay, new stress. If we stress in volume or pressure, remember that those two things are related, right? They have an inverse relationship. So if you increase the volume, you decrease the pressure and vice versa. So keep that in mind because those two go together in that both of these changes would impact your partial pressures. Now, if you have a change in volume or pressure of a system, the equilibrium will shift according to the number of moles of gas in the equilibrium scenario. So if you increase the pressure or decrease the volume, you're going to shift the equilibrium in the direction of the least moles of gas, right? That will relieve that extra pressure that has been applied, or at least it will minimize it. If you do the opposite, if you decrease the pressure or increase the volume, you'll shift the equilibrium in the direction of the moles of gas. If there is no difference in the moles of gas of a reaction, then changing the pressure or the volume will have no change at all because there will not be a shift that would cause that to have any change, right? Everything will be, the reactants and the products will be impacted in the same way because you're changing the partial pressure proportionately, and therefore your Q will not change, and therefore it will not deviate from the K. Now, one thing I do want to say here that I actually don't have on my notes is if you add an inert gas. So that means you have a system and you're adding a gas that is not going to react with any of the species that are present in equilibrium. That actually does not change anything because the partial pressures are going to be unchanged by that, right? So that can be very confusing for students to think about because they think that that changes the pressure, and therefore it's going to change the partial pressures, but it does not. So adding an inert gas does not cause a change in the partial pressures. Therefore, your Q is still equal to your K. So if you add an inert gas, there is no change to your equilibrium. Okay, so here's a little diagram for you. So in this case, we are, here's your reaction. The size in this graphic represents the number of molecules. If you decrease the volume, you can see what happens here. Your equilibrium is going to shift towards the right because here we have 3 moles of gas and here you have 2 moles of gas. And so what happens is that your blue and your pink increase in size and your green and your orange decrease in size because that is what minimizes the stress to the system. Okay, if you add a catalyst, adding a catalyst affects the forward and reverse reactions equally because if you look at this energy diagram, what happens is adding a catalyst decreases the activation energy, but everything else about the system remains intact. So because of this, going in the forward direction, going the reverse direction, both of those are changed in exactly the same way. Therefore, adding it does not cause your equilibrium to shift. It will speed up your reaction, but it does not change anything about your equilibrium. Remember, equilibrium does not indicate anything about speed. Okay, so this is a really nice summary table of Le Chatelier's principle. If you want to look at this more closely, I'm going to encourage you to pause the video here. Those of you that are following along with my notes, I have included a copy of this in my notes for you to review. And now I believe, yes, we are at a practice. So this is practice 10. So I've given you several situations regarding one reaction. So which way will the equilibrium shift in response to the changes below for the following reaction? Explain how the change affects the Q and K and how the comparison of Q to K changes. So again, just to be very clear, this is more, this question is more related to topic 7.10, but I didn't separate them out as clearly as AP does. So the AP program kind of treats 7.9 as a qualitative Le Chatelier's principle situation, where 7.10 kind of treats it quantitatively by calculating and comparing the Q and K. So go ahead and pause the video now if you want to try this on your own. I'm about to go through the answers. Okay, so looking at this reaction, if you add more into your reaction vessel, your Q is going to decrease, because what you have done is you have added more reactant. And if you remember, reactants are in the denominator, so that increases your denominator. When you have a larger denominator, that decreases your Q. Q is going to be less than K, and you're going to proceed towards the products to reestablish your equilibrium. If you increase the pressure of the surroundings, Q will also decrease, because what is happening there is that you are increasing the partial pressures. There are 4 moles of gas on the reactants. There are 2 moles of gas on the products. Because of that, that change in partial pressure has a larger impact on your reactants than it does on your products. So your denominator is getting larger than your numerator. Your Q is going to be less than K, and it will proceed towards the products. Again, that is specific to this. This is all specific to this reaction. But with this one, you have to pay close attention to the moles of gas. It is possible that changing the pressure is going to have no impact on your system if you have the same number of moles of gas on both the reactants and the products. But here we do not. We have a difference, and so we see an impact. Decreasing the temperature of the surroundings. This is an exothermic reaction, as symbolized by the positive heat energy there. So because this is an exothermic reaction, K is going to increase, and you're going to proceed towards the products if you decrease the temperature of the surroundings. Increasing the volume, and if you want to think about it that way, what I like to think about is if you decrease the temperature, then you need to bring it back up again by increasing the amount of heat that's being released. Increasing the volume of the surroundings. Increasing the volume decreases the pressure. As a reminder, that is an inverse relationship. So Q is going to increase, which means you're going to have a smaller denominator. That is because you're decreasing the pressure. And again, that impact is going to be larger in your reactants than it is in your products because you have more reactants. So decreasing your pressure has impacted your denominator more. Your denominator is getting smaller. Therefore, your Q is going to be Q increases. So your Q is going to be greater than K, and you're going to proceed towards the reactants. Okay, finally, adding a catalyst is going to be no change because your Q is going to be equal to your K. That's a dash. All right. So what should you be able to do with this? Well, really 2 things. You should be able to use Le Chatelier's principle to determine the shift in a system that responds to stress. And number 2, you should be able to describe the change in physical properties after a system responds to the stress. In other words, color, temperature, etc. What that means, if you have a reaction and it tells you that one side is, say, pink and the other side is purple, you should be able to look at the stress, determine if it's going to proceed towards reactants or products, and then determine what the color will be accordingly. So if it's going to proceed towards the reactants and the reactants are pink, then your color will go more pink. In another way, your temperature, back to the idea of if it's endothermic or exothermic, you got to decide if the temperature of the system will increase or decrease because of which side of the reaction is going to proceed to a greater extent. pH is another one that was specifically mentioned in the course and exam description. With that, you'll be looking at which side of the reactants or products contains the acid or the base. We'll get more into that when we get into Unit 8. That's it. I'm going to follow this up pretty quickly with another video talking about the Q versus K conversation, which we've gone into a lot in this video, but I'm going to kind of summarize it in the next one. And so I'll see you soon for that.